In today's video, we're going to talk about bonding specifically and how it applies with atoms and molecules. And we're going to have three questions here to discuss specifically about chemical bonds. So we're going to talk about electronegativity and how it actually works in molecular interactions. So the first three questions I want you to think about as we're going through this is, number one is, what does it mean to have a chemical bond? When molecules interact with each other, what is actually happening there? Number two, why do atoms bond with each other to form compounds? You know, if you take a look at things like water and salt, why does it actually happen? And the third question is, how do atoms bond with each other to form compounds? So we're looking at the mechanisms behind it and the rationale. So let's go ahead and dive in. So quick definition on chemical bonds, it's not a really simple way. You know, the way we think about bonds is that we talk about two atoms coming together, but reality there's actually a lot more that goes with it. It's not just put two atoms together and hopefully they're going to somehow stick together. There's actually a couple of forces that hold these atoms together, and what they do is that they tie these atoms to the hip, so to speak, and that is what allows them to have this molecule. And the bond is going to form if the energy of the aggregate is lower than that of the separate atom. So if I'm asking you, will this atom form a bond, we have to take a look at the energy profile of that. And most of the time we associate energy as either putting energy in or getting energy back out. So if it's lower overall, you're going to form a bond. And so the big question is, why is H2O H2O? Why isn't it H0, or why does it actually even occur? It's because of the fact that there's actually lower energy coming in. Let's talk about the two hydrogen atoms real quick. We have H atom, as you already know, it's a very small atom. And usually they are moving at a very fast rate because hydrogen is a gas. And usually they don't have any sort of interaction. However, if the atoms begin to get very, very close together, you begin to see that they form the H2 molecule. And by definition, a molecule is described as two atoms coming together, sharing or transferring electrons. And because of this, there's an optimal distance in which they're going to achieve that overall energy of a system. And so when we take a look at hydrogen as an example, you really want to think about that distance that we're talking about, that space. Here is the energy profile for bond creation. Now, if you take a look at the x-axis and the y-axis, you can tell that the distance between the bonds are in nanometers. So if I were to measure the distance between hydrogen from each of those, I could see that the potential energy in kilojoules per mole, as it increases, it seems to be not as favorable. So taking a look at the one on the left here, the distance is greater. You can see that the hydrogen molecules are not going to combine. And this kind of makes sense, right? It's just basically how close are they going to be able to get together. Now, on the left-hand side, what you're starting to see is hydrogen having a bond length of 0.074. And in this case, what you see is an optimal length where the energy is low. It's negative 458 kilojoules per mole. And this tells me that hydrogen here would actually form that bond. So usually what you'll see in energy profile diagrams is a lower energy for specifically these type of molecules. And that's the reason why you always want to look at energy versus no energy. Now at zero, you're not going to get those bonds. So a couple of key ideas in bonding is, number one is ionic bonding, which means that electrons are transferred, meaning that they are being given or receiving. There's also covalent bonds, which the electrons are shared equally. And we're talking about, what about stuff in the middle when you don't have sharing or transferring? And there's actually a couple of cases, which we'll talk about that in a second. All right. Polar covalent bond is when you have unequal sharing of electrons between atoms in a molecule. So one of them is tugging on the other harder. I like to think of it kind of like a unequal relationship, right? Where someone says, I really want this more than the other. And it results in what they call a charge separation, where a partial positive or partial negative, because someone's tugging on that electron more, the atom is tugging on that more, the other atom is going to end up getting a more negative charge than the other atom that now has a positive charge. So this partial charge is important because it explains a lot of things later down the road. Now here's a way to explain this a little bit better. Take a look at hydrogen fluoride molecules, which is HF, and we denote that using this delta charge here, negative and positive for the partial charge. And what you could see is if you apply an electrical field which is composed of negatively charged particles, the atoms are going to attract in one way than the other. So what's going to happen here is if you apply the charge, the positive side of that molecule is going to attract to the negative side, or the cathode or anode, and the negative side is going to attract to the positive side. So by doing that, we're going to basically be able to prove specifically that there is some sort of polarity or polar charge on it, based off of the way it attracts on this side. So we're taking a look at the negative side. You can see that there's this actually hydrogen here, which is positively charged. It's going to want to get attracted to that negative, and that negative charge here, it's going to get attracted to that positive side. So they're going to start sticking to different parts of that wall there. Now let's talk a little bit about just again this idea for chemical bonds. What is meant by the term chemical bond? So it's basically the joining of these two electrons that are going to have a smaller distance and they're sharing or transferring electrons. Why do bonds bond with each other to form molecules? It really has to do with the idea of energy. The lower that energy is, the more likely they're going to have that bond. And how do they bond? They're going to form two types of bonds, ionic and covalent bonds. But again, you can also have something in the middle, like kind of like a polar covalent, where there's a partial charges. And ionic, as you already know, it's something where we're transferring electrons, and covalent where we're sharing those electrons. Now let's talk about electronegativity real quick. The electronegativity is a concept that has to do with the ability of a molecule to attract shared electrons. So it's not talking about the atom specifically. It could also be talking about a molecule. And when we're talking about a molecule, for example, HS, like a hydrogen and a chloride or hydrogen and a fluorine, there's going to be electronegativities associated with each of the atoms. For example, H and X. Also, there's going to be this bond energy that's expected with that. So what we're doing is we're trying to compare what the overall electronegativity is for that molecule by comparing how well each atom is going to pull on those electrons. As a general rule, the electronegativity generally increases across a period and decreases down a group. Now, the word generally is general, meaning that there could be exceptions to this rule, and it's not always ironclad. So just keep that in mind. We're looking at trends that there's always going to be some sort of element that may buck this, but that's usually for the most part. So we're taking a look at electronegativity values from 4.0 to 0.7. Notice carefully there are no units on this. And this is something that's always been kind of debated about what the units are, but it's a relative scale, so you're really comparing between elements. So 4.0 is the most electronegative, so we're all comparing it to fluorine, and cesium is going to be the least electronegative for 0.7. So keep that in mind that you're always using a relative scale to fluorine. Now, the electronegativity values from Pauling, so there was a whole story with Pauling about how he came up with these numbers, so just, if you want to research a little bit more, you can, but generally speaking, if you take a look at period 1 as an example, we're talking with lithium all the way down to fluorine, you can kind of see the electronegativity for fluorine is 4, so it's pretty much dominating the entire, periodic table in terms of pulling those electrons out. Hydrogen is kind of like a 2.1, so we kind of put it off to the side a little bit because hydrogen is located right here, but because it's a 2.1, we're going to move it a little bit closer to the side. So hydrogen is going to be one exception to that rule, so just kind of keep that in mind. Now we're getting down to chlorine and bromine. You can kind of see that as you're going down a group, it drops. So, when I say generally, there's a couple exceptions, because if you take a look at something like manganese as an example, it has a 1.5. So the transition metals are a little bit weird because they kind of start going up and down. So generally the trend is up, but again, just as I was explaining earlier, you always get those exceptions to that rule. And there's a couple of things in here like silver and cadmium, it kind of goes down and it kind of jumps back up again. But if you go past the transition metals, for the most part, you should start seeing the trend go back again. So if you go out from boron to fluorine, aluminum to chlorine, and then these other last three right here, you can kind of see that going up. At the bottom, it generally, follows that, but these are the ones that are kind of a little bit on the exceptional rule. All right, so let's do a quick check. If you want to pause this video, go ahead, and just so that you can test yourself. So if lithium and fluorine react, which one has more attraction for an electron? So this is a really quick, simple answer. I mean, it's going to be fluorine, and fluorine is because the nuclear shell for fluorine is a lot higher. So if you take a look at the number of protons for fluorine, it's going to be a lot more than lithium, even though they are in the same period. And because of that, the attraction to the electron is going to be higher. And, very similar to ionization energy trends. In a bond between fluorine and iodine, which one has more attraction? And again, it's going to be fluorine, because as you're going down a group, the electronegativity trend decreases. And the reason why it's because you have increased shells as you're going down a group, which causes electron shielding and also reduces the attraction between the protons and the electrons as you're adding in more orbitals. All right, so fluorine's going to take the cake for that. Okay, so what is the general trend for electricity across rows and down? And basically what I was explaining earlier, so if you're going up and down, the trend decreases, down a trend, and then left to right it increases because of both shielding and also increased nuclear charges across a period. All right, let's talk about electronegativity and bond type. So basically what it comes down to is you have electronegativity differences between two different atoms, and usually you take both values. So you take two elements and you subtract them, 0 to large. And you're talking about covalent characters. So if I have something like a carbon and a hydrogen, which is a covalent, two nonmetals, you have a zero, almost a zero type of electronegativity difference, because these are usually going to be very close in charge. Now, as you're getting to ionic characters, the differences are larger and your electronegativity differences are greater. So something like sodium chloride, as an example, would be two extremes. Sodium, which have a low electronegativity, and fluorine, giving a high electronegativity difference, and the bond is usually generally going to be ionic. All right, so let's do an exercise real quick. Go ahead and rank the bonds from most least to polar. All right, take a minute or two and see if you can do that. Okay, so if you did that, then your answer choices should be the following. So if you take most least to polar, so if you're taking a look at polarity, you're going from high to low. Okay, so you're going for A, it would be the most polar would be CF, and then OF, and that kind of makes sense because oxygen and fluorine have very similar electronegativity values, while carbon and fluorine are a little bit on the opposite side. Number B, you have silicon and fluorine versus nitrogen, and so again, it's the placement of the elements in the periodic table that will dictate which one is more polar. The more opposite sides you're going to get between these two elements, the higher that polarity is going to be. All right, now considering these 5, go ahead and pause the video and see if you guys can figure out which one is least polar. And so MgO, CO, OO, SiO, or NO. Okay, so if you take a look at NO, NO is going to be the least polar. Again, going to the same idea, the least polarity meaning that you're going to have less of that difference. So nitrogen and oxygen are very close to each other. So that's basically going to be it. And which of the following would be most polar without being considered ionic? So, when you talk about ionic, so go ahead and take a moment of that and I'll explain this later. Okay, so when you're talking about ionic compounds, you're really talking about this idea of really big extremes. And you're talking about being polar, but not necessarily purely ionic. It's got to be one of these. And so you're looking for something like in the middle. You're not looking for something that's really close electronegativity value, but not to the extreme, but something like straight down the middle. So if you calculate each one and you say to yourself, all right, where's the location of those? The only one that makes sense is going to have to be SiO. Because if you take a look at oxygen, well, obviously that's more like a covalent one. Obviously, they're same electronegativity values. MgO, they're on the far extremes. Then if you're talking about NO and CO, you're talking about, obviously, these two are going to be in the same group, but you're taking a look at this one's a little bit further down because it has less electronegativity than CO. So you're really looking at silicon and oxygen there as being polar. All right, now, sorry, one last thing here. I also want to mention that if I ask you which one would dissolve in water, you can basically predict that by looking at polarity. So one thing I always try to tell people is, okay, so now that you know which is polar and which is nonpolar, how could you use that in a problem? And one of the ways you can do that is you can predict the solubility. So if I ask you out of these 5, which one would be most soluble in water, you probably would say SiO. Which one would be more soluble in a nonpolar situation? Then you could possibly pick an OO as an example. So there's actually different ways in which you can use these type of questions, and also taking a look at properties like melting points, boiling points, things like that, because polarity will change the ability of those forces to be able to escape, your liquid phase and your gas phase and so on. So we'll talk a little bit more about those later down the road. All right, guys, that finishes the electronegativity section.